right, so just to kind of properly introduce this chapter here, we kind of have combined these two chapters together. So this is chapter 20 and 21 on carboxylic acid derivatives. All right, so first of all, functional groups that we're discussing here, we have the namesake of the chapter are carboxylic acids. Carboxylic acids being another carbonyl-containing functional group. All right, but importantly, bonded to that carbonyl carbon is a hydroxyl group. All right, so these are our carboxylic acids. All right, and as the name implies, these are organic acids. When you add them to water, they indeed make that solution acidic because they have these donatable protons here. All right, so we can donate this proton from our carboxylic acid, making it an acid. All right, if we want to draw that structure that we get after this proton is donated, right, we would take our carboxylic acid, we would remove a hydrogen and replace it with a lone pair. Okay. These deprotonated carboxylic acids here also kind of have fancy names. Our carboxylic acid is when it has its proton. After it loses its proton, it becomes a carboxylate ion. And you'll hear me throw around that term quite a bit, so let's just put it down here. This is what we call a carboxylate. Okay, so we talked about these carbonyl-containing functional groups a bunch, and we talked about aldehydes and ketones, and now we're going to talk about these what we call carboxylic acid derivatives. And the big difference is what we're going to do is we're going to be swapping out this hydroxyl group for some other electronegative atom, all right? That's what distinguishes our carboxylic acid derivatives from our aldehydes and our ketones. Remember, if it's an aldehyde, there'd be a hydrogen bonded to this carbon. If it was a ketone, it would be another carbon atom bonded to that carbonyl carbon. Our carboxylic acid derivatives are we're going to be swapping these out for other electronegative elements. All right, so first one that we're going to talk about is if we swap it out for one of those electronegative halogens. So we're just going to put generic X here, where X is some halogen. All right, these are what we call acyl chlorides, or rather acyl halides. All right, if we take our carboxylic acid, we're going to keep that oxygen, but instead of having it be a hydroxyl group, we're going to put an alkyl group on the other side. These are what we call esters. All right, if we take that ester and we swap it out for oxygen's other family member, sulfur, we get what's called a thioester. All right, and if we take that oxygen, our carboxylic acid, and we take that hydroxyl group and we replace it with a nitrogen, we get an amide. All right, not an amine, which is when we don't have our holy crap, carbon-oxygen double bond, carbonyl, there it is, holy cow. When we don't have our carbonyl group, we call those amines. When we do have our carbonyl group, those are amides. All right, and then last one is going to look a little funky. We're going to take that carboxylic acid. We're going to keep that oxygen, but on the other side is going to be yet another carbonyl group. These are what we call acid anhydrides. All right. So our carboxylic acid derivatives, we have our carboxylic acid with that hydroxyl group, or our derivatives are when we replace that hydroxyl group with some other electronegative atom. All right? And what we're going to find is that we can swap between these functional groups here, right? We can convert an acyl halide to a carboxylic acid or vice versa. We'll talk about those reactions here in a second. We're going to focus on the namesake here, carboxylic acids, and we're going to talk about these reactions that we've discussed previously on how we prepare carboxylic acids. All right, so there are a few reactions that we talked about of preparing carboxylic acids that all fell under this umbrella of oxidation reactions. All right, so we talked about how we could take a primary alcohol and oxidize that to a carboxylic acid. All right, and truthfully, there are quite a few different oxidation agents that you could use that would accomplish this. The one that I've been testing you on, our strong oxidizing agent, was that sodium dichromate. All right, you have to do that under these acidic conditions, dilute sulfuric acid. Okay, so we can oxidize our primary alcohol to a carboxylic acid. We didn't have to start with an alcohol, though. There's another functional group that we can oxidize to a carboxylic acid using these exact same conditions here. That would just be an even more oxidized starting point here. So instead of having a carbon-oxygen single bond, we're going to replace that with a carbon-oxygen double bond. All right, and what did we call these? Aldehydes. All right, so either our primary alcohols or our aldehydes, either of those can be oxidized using that strong oxidation agent sodium dichromate to a carboxylic acid. All right, and then there was one more that fell under this umbrella as well of oxidation reactions, but it was kind of weirdly tucked in that aldehyde and ketone chapter. That was when we start out with a carbon-nitrogen triple bond. All right, if we treat this with dilute acid and heat, we get a carboxylic acid. All right, these compounds here are a little weird because outside of organic chemistry, in organic chemistry, they're called cyano groups, but in organic chemistry, they are called nitriles. Those carbon-nitrogen triple bonds. Cool. So these we covered before, these oxidation reactions. We can convert a primary alcohol, an aldehyde, or even a nitrile into a carboxylic acid. All right, we're going to learn another way to do it. This is going to be using a familiar reagent here, a Grignard. Right, Grignards are those organometallic compounds, specifically that magnesium bromide in that compound. And so we're going to do a reaction that we've seen before. We're going to react this with an aldehyde or ketone. In this case, we're just going to pick that smallest possible aldehyde, formaldehyde. All right, everybody's going to take a second and remind ourselves here, what is our nucleophile and what is our electrophile in these reactions? Take a second looking at our chemical equation here. What's your nucleophile? What's your electrophile? All right, our Grignard reagent here is which one? Our nucleophile or our electrophile? They are nucleophiles, specifically at that nucleophilic carbon. Carbon, usually not a very electronegative atom. We don't usually think of it as an electronegative atom. But in a bond with a metal, which is very weakly electronegative, it's pulling that electron density onto itself, giving us that nucleophilic carbon. All right, so then our aldehyde here is our electrophile, and what's our electrophilic site? That carbonyl carbon. All right, so our nucleophile is going to attack our electrophile. Remember, an easy way to get a point off here is by trying to start your arrow at this carbon atom. Our arrows must start at a pair of electrons. So I have to start it at that carbon-magnesium bond. And when that electrophilic carbonyl carbon gets attacked, we don't break its octet. It kicks that pair of electrons up onto that oxygen. All right, so now I have my 3 carbons from my Grignard. I'm going to draw my new carbon-carbon bond. So what must live on the other side is that electrophilic carbon. And it's got that oxygen that's accepted that extra pair of electrons and has that negative charge. All right, so this thing here, when our carbonyl carbon gets attacked, I'm going to put in these other bonds just to make it clear here. These are what we call these tetrahedral intermediates. All right. We talked about them with regard to reactions of aldehydes and ketones because they form anytime a carbonyl carbon gets attacked. But then we also talked about esters a little bit last chapter as well, and how all of a sudden in those esters, when we formed our tetrahedral intermediate, we had this good leaving group on there. And that's why we had these different reactions of esters than we saw for aldehydes and ketones. We had our Claisen reactions versus our aldol reactions, all right? And we want to get in the habit of doing that in this chapter in particular, looking at these tetrahedral intermediates and asking ourselves, do we have a good leaving group, okay? So in the case of this molecule here, a carbon or hydrogens, there is no good leaving group, all right? Nothing that we can kick off. So instead, we're stuck. We're stuck at this alkoxide step until we do our second step in our reaction, that acidic workup. All right, so if there's no good leaving group, we're stuck, and all we can do is protonate that oxygen. All right, we got some dilute acid in there. We're going to protonate, and that will form our alcohol. All right, so this was this Grignard reaction that we learned before. This was a method of converting our Grignard and our aldehyde or ketone into an alcohol. All right, but we said that this was a preparation of carboxylic acids section here. And we're going to use a Grignard to do it. So what we're going to do is we're going to be clever. And instead of using an aldehyde or ketone, we're going to use that same nucleophilic Grignard. All right, but now I'm going to treat this with a compound here that has not one carbon-oxygen double bond, but two carbon-oxygen double bonds here. All right, technically not even an organic molecule. What is this? Carbon dioxide. All right, so we treat our Grignard with CO2. We are going to see same exact thing. Our carbon-oxygen double bond leaves that carbon electrophilic. So that carbon is still our electrophilic site. Our nucleophile attacks our electrophile. We don't want to break carbon's octet. All right. So if we draw our intermediate here, we have our new carbon-carbon bond. Importantly, this is a method of creating a carboxylic acid that gives you a new carbon-carbon bond. So our carboxylic acid product has one additional carbon. All right. So this first step here makes these molecules, we talked about what these were called. What do we name these things here when we deprotonate a carboxylic acid? Carboxylate. All right, so we get a carboxylate ion that forms. And then we're going to do that same second acidic workup step. And we'll protonate that carboxylate ion to form a carboxylic acid. All right, so this is a method of using a Grignard, getting a new carbon-carbon bond when we treat that Grignard with carbon dioxide, giving us a carboxylic acid. Cool. All right, so we had a few methods of creating carboxylic acids using what we called oxidation reactions, where we create more carbon-oxygen bonds. We also have this new method here using a Grignard and treating it with carbon dioxide as a way of creating a carboxylic acid as well. All right, so now we're going to look at all of our carboxylic acid derivatives, and we're going to rank them according to what we call our reactivity. All right, what we're going to do is we're going to take all those carboxylic acid derivatives. We're going to rank them from the most reactive to the least reactive. And we'll talk about what that means to be more or less reactive here in a second. All right, so our most reactive carboxylic acid derivative are those acyl halides. Okay, these ones are the most reactive of all of our carboxylic acid derivatives. what we're going to see is that means that it's easy to convert these acyl halides into any of our other carboxylic acid derivatives, all right? So we can convert something more reactive into something less reactive. Since acyl halides are the most reactive, they can be converted into all the other carboxylic acid derivatives. All right, the next one on our reactivity list are those acid anhydrides. All right, so that's that oxygen that's sandwiched between those two carbonyl groups. All right, since these are less reactive than acyl halides, I can convert my acyl halide into an acid anhydride. I can't go the other way. All right, and we'll talk about how we do that here in a second. Let's just continue to put these down on our list here. All right, the next one are our thioesters. Thioesters are less reactive than acyl halides and acid anhydrides. All right, going down the list here, the next ones, these are actually tied. We have our carboxylic acids. All right, and these are just as reactive as if we replaced that hydrogen with an alkyl group or our esters. So these two we're going to put on the same level here because they're tied. All right, that's our carboxylic acids and our esters. All right, and then the last one on our list, our least reactive, is when we replace that oxygen with a nitrogen, our amides. All right. What we've done is we've taken these carboxylic acid derivatives and we've ranked them from most reactive to least reactive. All right, again, what it means to be most reactive is that we can convert from, let's say, our acyl halide into any of these less reactive carboxylic acid derivatives fairly easily. All right, so how are we going to do it? Well, let's take a specific example. We're going to convert our acyl halide into a carboxylic acid. All right, so let's see if we can't figure out what's going on. All right, let's put our two compounds that we want. I'm going to pick a specific acyl halide. We're going to pick an acyl chloride here. And our goal is to convert this into a carboxylic acid. All right, so how are we going to do it? Well, let's just balance our chemical equation here. Over on this side, I'm going to need a chloride ion to balance everything out. What would I need to add on this side in order to balance everything out? I'm just doing a simple substitution here, substituting that chlorine for that hydroxyl group. So what else am I going to include? A hydroxyl, all right? If we included hydroxide, we can convert that acyl chloride into a carboxylic acid, all right? It's the name of the game here. We're just looking at what it is that we're substituting. That's going to be our nucleophile in these reactions, all right? Now, in the case of hydroxide, this is pretty cheap and readily available, but these reactions work so well. So actually, before we even talk about the reaction, let's figure out what's going to be our nucleophile and what's going to be our electrophile. Everybody take a second and try to identify nucleophile and electrophile, and then specifically your nucleophilic site and your electrophilic site. All right, which one's which here? What's my nucleophile going to be? And how can we spy that that's our nucleophile? Because that negative charge. All right, so specifically that oxygen's going to be my nucleophilic site. What's my electrophilic site? That carbonyl carbon. All right, and this is an even better electrophile than it was when we were talking about aldehyde and ketone carbonyl carbons. All right, because not only does it have this oxygen pulling electron density away from it, it also has this halogen, or whatever that electronegative element is, pulling electron density away from it. So these are really good electrophiles. So good, in fact, that we don't have to use our strong nucleophile. We can use our weak version where we protonate it. So our neutral, in this case, water nucleophile. You could use hydroxide, it's just kind of overkill because something that's always going to be cheaper is the neutral version of whatever nucleophile it is that you're talking about. All right, so what we're going to do here is our mechanism. We're going to show that nucleophile, our weak nucleophile water. That lone pair is going to attack that electrophilic carbonyl carbon. All right. This gives us that world famous tetrahedral intermediate. All right, and we said that when we got to these tetrahedral intermediates, what were we going to ask ourselves? Do we have a good what? Do we have a good leaving group? All right, do we have a good leaving group here? Yeah, we actually got two. We could kick off water, but where would that take me? Right back to where we started. So we're going to indicate that this is indeed a reversible first step here. Yes, that does happen where it just bounces right back to where we were. But if we're going to do our productive step forward here, that lone pair is going to come back down, and we're going to kick off that halogen leaving group. Right? Kick off that chloride ion. So that reforms that carbon-oxygen double bond. We got rid of our chloride. We're almost there. We're almost at our carboxylic acid. We've just got an extra proton on there, right? Because we started out with our neutral nucleophile. We're going to have this last deprotonation step. In order to deprotonate, we're going to need to use some base to do it. All right, we'll talk about what base we use here in a second. But for right now, let's just finish off this mechanism, deprotonating that oxygen, giving that pair of electrons back to that, back to the oxygen, creating our hydroxyl group. All right, so now last step here, depending on your carboxylic acid derivative that you start with and your nucleophile, the identity of this base might be a little different. So let's just note here, this is our base that we're going to use. Well, you got two potential bases floating around in this solution. We have our nucleophile, our water, can play the role of a base, but we also have our leaving group here, our chloride ion. All right, so for our base, it's either going to be your nucleophile or your leaving group. All right, whichever is the stronger base. Yeah, so in this particular case, with our alkyl halides here, our nucleophile, our water molecules, I'm sorry, not our alkyl halides, our acyl halides, and our leaving groups are going to be those halide ions. All right, in this case, your halide ion is not a good base. Your water molecule is a little bit stronger. So if we're doing this particular reaction mechanism, we're going to be using as our base that nucleophile water. All right, if it was any other carboxylic acid derivative, though, what we would find is that leaving group would be our stronger base, and that would play the role of our proton acceptor in that last step. All right, last thing that I'm going to note here about this mechanism is that these two steps here are interchangeable. It wouldn't have mattered if you deprotonated this oxygen first before you had your tetrahedral intermediate collapse, or if you did your tetrahedral collapse first. Either one of these steps I would accept first. There's sort of some good reason to believe that with our acyl halides in particular, you have tetrahedral collapse first before that deprotonation step, but that's not always the case here. So I would accept either one of these, or rather in either order here, these two steps. We need a tetrahedral collapse, we need a deprotonation step. Whether you swap those two orders, I'd be fine with that. Cool, so I guess if we're being good here, our last product are those hydronium ions. Cool, all right, so like we said, we can go from something more reactive to something less reactive, and in order to go from our acyl halide to our carboxylic acid, all we needed to do was add water. So then let's try to fill out the rest of these here. How would I go from an acyl halide to an ester? What would I need to add? All right, what we're going to do is we're going to take that group that we're trying to swap out here. Boom. And like we said, we could use our strong nucleophile version, but that's kind of overkill. We could just use our neutral version. So I'm going to protonate that, creating what? What's our functional group here? An alcohol. So if we treated our acyl halide with an alcohol, we would get an ester. All right. What about a thioester? How would we get that? Same idea. Let's copy that new functional group on there. Let's protonate it. All right, what do we call these? Like alcohols, but with sulfurs? Thiols. All right, depending on what my alkyl group is, we're going to say R, SH, because I could have used any alkyl group. All right, same thing for my amides. I'm trying to replace that chlorine with that nitrogen, so I'm just going to use that protonated, in this case, ammonia, NH3. That's really messy. All right, the one exception here to using all these neutral nucleophiles is going to be to create this acid anhydride. You would take this and you would protonate it to make a carboxylic acid. That's just not a good enough nucleophile. I'm going to be good and put my lone pairs here. So instead we have to use that negatively charged carboxylate ion. Oops. All right, but we can go from that more reactive acyl halide to these less reactive carboxylic acid derivatives by simply adding in whatever that leaving group or whatever that new functional group is that we're trying to create. And we can do this for all of them. So for example, how would I go from a acid anhydride to one of those more, less reactive functional groups like a thioester, a carboxylic acid, a regular ester, or an amide? All right, playing the same game. If I took that acid anhydride and added in a thiol, I would get a thioester. If I added in water, I would get a carboxylic acid. And if I added in an alcohol, I would get an ester, or ammonia to get that amide. All right, continuing this same game, we could create a thioester into a carboxylic acid, a regular ester, or an amide by adding in water, or an alcohol, or ammonia. All right, so we can convert something more reactive, something higher on our list, to something less reactive using whatever our neutral version of our nucleophile is. All right, so for a carboxylic acid, we'd be using water. For an ester, we would be using an alcohol. Thioester, unthiol. Acid anhydride, that carboxylate, and our amide, we would use an amine. All right, now there's one sort of flaw in this whole logic here, and that is going between these last two steps. All right, it turns out that you cannot convert a carboxylic acid into an amide, at least not using this simple method that we've been talking about. All right, this does not work. Okay, so why is that? Let's look at these two in particular here. All right, so carboxylic acids to amides. Okay, so let's put down for a second this balanced chemical equation. All right, our carboxylic acid being converted to an amide. All right, and I told you that it's not going to work, but let's say just using the same logic of what we saw above with all of those reactions. What reagent would I use to do it? Ammonia, right? So I would take my my amide functional group here, that NH2. I would protonate it. Boom. Okay. This is what we would call a nucleophilic substitution reaction. I'm using a nucleophile. I'm substituting out that hydroxyl for that NH2. So this would be a nucleophilic substitution reaction. But again, we do not get nucleophilic substitution that occurs here. This would not be my product of this reaction. All right, so why is that? Well, in order for a nucleophilic substitution reaction to happen, our ammonia is going to be a nucleophile, and that carbonyl carbon is going to be our electrophile, and our nucleophile attacks that electrophile. All right. The problem is that a carboxylic acid has an even more accessible electrophilic site. That's what gives its name of being a carboxylic acid. It has this acidic proton. All right. So rather than our nitrogen attacking that carbonyl carbon, our nitrogen is simply going to attack that proton, and we're going to get a simple acid-base reaction. Acid-base reaction happens much quicker than any nucleophilic substitution reaction. All right, so what does happen instead is a simple acid-base reaction. So what we're left with is a carboxylate ion. And our protonated nitrogen, or an ammonium ion. All right, and after this simple acid-base reaction occurs, our carboxylic acid on our reactant side, this was a good electrophile, but as soon as I've deprotonated it, now all of a sudden that pair of electrons jumping back and forth, this thing is not an electrophile anymore. Not only that, but nitrogen, when it forms that new nitrogen-hydrogen bond, it loses that lone pair. So this ammonium ion here is not a nucleophile. All right, so instead of having a nucleophilic substitution reaction, you have this much quicker acid-base reaction occurs, and that kills your electrophile. Our carboxylates can no longer play the role of an electrophile, and our ammoniums can no longer play the role of the nucleophile. So you don't get your expected nucleophilic substitution reaction, you just get this acid-base reaction, and then you're stuck. All right, so we can't go, even though carboxylic acids are less reactive, rather more reactive than our amides, we can't do it. Instead, we would get a simple acid-base reaction. All right, and you can technically go from an ester to an amide here using that expected nucleophilic substitution reaction. All right, but in practice, this reaction doesn't work very efficiently. All right, not a great way to do it. So then how am I supposed to go from this level down to our amide? Well, fortunately, there is one way that we can go backwards here. All right, so we can convert a carboxylic acid all the way back up to that most reactive acyl halide. All right, so we got one way to go back up this map here. All right, and that is using a familiar reagent that we've seen before, SOCl2, or thionyl chloride. All right, so our one way to go back to create something very reactive, we're going to convert from a carboxylic acid into that acyl, specifically an acyl chloride, using thionyl chloride. All right, so first of all, we've seen thionyl chloride before, and that was when we were talking about converting primary or secondary alcohols into alkyl halides. All right, that was one method of getting rid of that hydroxyl group and replacing it with a good leaving group. Was using thionyl chloride. Oh, sorry, SOCl2. All right, it turns out that if instead of starting with an alcohol, you started with a carboxylic acid. All right, so I take that same thing and I'm just going to put a carbonyl bond on there. Turns out it'll do the exact same thing. It will replace that hydroxyl group with a chlorine. What's up?
Did you do a backside attack, or is that only when stereochemistry is already involved?
Yeah, so you would have to use, so you don't have any, I guess just to back it up, you're right. There was this whole stereochemical inversion that happened when we were talking about reacting a secondary alcohol with our thionyl chloride. We do not have that same problem when we're starting out with a carboxylic acid because it doesn't have that tetrahedral geometry. It has that trigonal planar geometry. So there's no stereochemistry that we have to worry about with that second reaction there. All right, so that means that if I did want to create my amide from my carboxylic acid, I could do it. I just wouldn't be able to do it in this one step here. All right, so if we did want to create an amide from a carboxylic acid, we would just first convert that carboxylic acid into an acyl chloride using thionyl chloride. And then in a second step, now we have that super reactive acyl chloride, so then we could just add in our ammonia in order to create our amide. All right, so if we tried to add ammonia off the bat, we get our acid-base reaction. We're instead going to first convert to an acyl chloride, and then we can add an ammonia to get our amide. Cool. All right, so we have these carboxylic acid derivatives. We ranked them from our most reactive to our least reactive, and we talked about converting from more reactive to less reactive, and now we learned we got that one way that we can go back. All right, we'll pick up with this next time.